Okay, our sixth subtopic, which is torque on a coil. We have to use torque and then explain briefly the working principles of a moving coil galvanometer. Okay, so torque on a coil. So this is a very long explanation. So this is basically the derivation on how did we obtain the equation for torque. Okay, so let's consider a rectangular coil ataupun a loop of wire with side lengths of A and B. Okay, so they have the length of A and B. Okay, so we can turn that into axis PQ. The coil is in magnetic flux and the normal coil makes an angle of theta with the direction of the magnetic field. Okay, so from the figure here, the magnitude of the force is given by this equation here. So we get this equation after simplification. So from figure 25 on the left, the forces F lies along the PQ axis. Okay, so it lies along the PQ axis and the resultant force on the coil is 0. However, the net torque is not 0 because the forces F1 are perpendicular to the axis PQ. Okay, so they are perpendicular to the axis PQ. Alright, so the force F1 causes the coil to rotate in clockwise direction. So it's gonna be rotating in clockwise direction about the PQ axis saja. So maksudnya yang ni dia terbalik-terbalik, bukan terbalik, they're rotating begitu-begitulah. Alright, so it is given by this equation here. Hence, simplify it, so we will then get this equation here. Okay, for a coil of specific number of turns, we can just times it, multiply it with the number of turns lah, in order for us to get the value of torque on the coil. Okay, so the theta here is the angle between A and B. Okay, vector area and magnetic flux density. Okay, so the torque will be 0 when theta is equal to 0 and will be maximum when theta is equal to 90 degree. Okay, so when a question asks what is the maximum torque, remember theta should be equal to 90 degree lah. Okay, so it applies to not only torque, to the rest of the previous subtopic when it applies. Okay, so in a radial field, the plane of the coil is always parallel to the magnetic field for any orientation of the coil. Okay, so hence the torque on the coil in a radial field, remember in a radial field, for example a moving coil galvanometer, it would always be constant and maximum. Okay, so that's the hint there. You need to remember for a torque on a radial field ataupun moving coil galvanometer, the torque will be constant and maximum. Okay, so we will be straightly gonna use the equation here. Okay, that is for radial punya coil lah. Okay, alright, now moving coil galvanometer. So a galvanometer consists of a coil of wire suspended in the magnetic field. For example, based on this figure here lah, this is the moving coil galvanometer. Okay, so the coil is in rectangular shape and it consists of many turns of wire lah. So when the current flows through the coil, so other current flows through here, the magnetic field will exert a torque. Remember, torque untuk radial ataupun moving coil galvanometer, we will straightly ahead use this one. So the torque is then opposed by a spring which exerts a torque due to spring lah, which is given by this equation here. Okay, so K here is the torsional constant, whereas the theta is the rotational angle of the coil in radian. Okay, remember it is in radian. So the coil and pointer will rotate only to the point where the spring torque balances the torque due to magnetic field. Hence, tau is equal to tau s lah. Okay, for the spring torque due to the coil and torque opposed by the spring. So this would gives us the not magnetic field. It would gives us the current. Okay, all right. So that is basically the theory part for our sixth topic, which is torque on a coil.